Okay, great. So let me get right into it. Good morning, good afternoon, or I guess good evening, everyone, depending on where you are. I'm going to be talking about transcranial electrical stimulation, really transcranial direct current stimulation, and how focal we could be with it and how well we can optimize it. And these are my disclosures and the sources of support, and the slides and references already. The slides you can find online on Twitter, as well as a link to where all the papers are. So just some general opening thoughts in these times. Obviously, I hope everyone is staying well and staying safe. One silver lining to what we're going through is this reminder that we really are all in this together. And I wanted to thank Brainbox for putting together this event, which is a way for us to come together and to keep moving forward, which is really the last point I want to make. A lot of us have a lot of other things on our mind right now, but it's very important to remember that the work that we all do with brain stimulation, whether it's research or working to make it available therapeutically, is more timely now than ever. All right, so there's different forms of neuromodulation technologies. I think this audience is well aware of the different types of brain stimulation platforms. Ranging from invasive technologies that would require a surgeon to implant a device to non-invasive technologies that, again, I know people are familiar with here, like transcranial magnetic stimulation, electrical convulsive therapy, and the kind of technologies I'll be talking about, which is transcranial electrical stimulation. And I like to kind of classify these as technologies that are implanted, so they do require surgery. Technologies that, at least in their current form, really require you to be at the, sorry about that. Oh, sorry. Technologies that require you to be at the medical center, that would be TMS, obviously ECT, and then this last class of technologies, which is wearable technologies, of which transcranial direct current stimulation is one of them. So I'll be talking about that. I'm sure this audience is familiar with transcranial direct current stimulation. Involves applying electrodes on the scalp and passing a weak current through them. It is pretty unique among the neuromodulation approaches in that it uses direct current and not pulses. And it is a very popular technique. I think it's arguably among the most investigated techniques, interventional brain techniques for changing brain function, both across healthy subjects and across clinical populations. And we're all aware of the rate of publications and research activity around tDCS. Again, I'm sure this audience is familiar with what tDCS looks like. This is what it looks like on my head with 2 electrodes. There's always at least 2 electrodes, always at least 1 anode, and always at least 1 cathode. The anode is in electrical stimulation, the positive electrode, and the cathode is the negative electrode, and current flows from positive to negative. You see the cables going down the side of my head. You don't see they're connected to a device. A tDCS device is certainly not a 9-volt battery, but it can be powered by 9-volt batteries, and a 9-volt battery is roughly how much voltage you need in order to apply tDCS. tDCS is current controlled. It's a few milliamps, typically 2 milliamp, tens of minutes, typically 20 or 30 minutes, and depending on the intervention would be applied once or multiple times per week, or even over several weeks. And you often hear the terms anodal and cathodal tDCS. It's important to remember you always have the anode, you always have the cathode. So when we talk about anodal or cathodal, we're actually talking about whether the region of interest or the hypothesized brain region of interest is near the anode or near the cathode. So if the target is near the anode, we'll call it anodal. If the target is near the cathode, we'll call it cathodal. But there's always anodal and cathodal going on at the same time. And I've shown you an example of tDCS applied with regular pads. We're also very interested in applying tDCS using small gel-filled electrodes, and we call those high definition electrodes, or HD tDCS. And what I'm showing you here are results of a computational model. This is an MRI derived model, so it's an individualized model. It's of my head. And you can see that it's relatively realistic. And on the one side, you're seeing the simulation of the M1 SO montage. And then the other side, you're seeing the M1 SO regular pad tDCS montage. And on the other side, you're seeing a simulation of the 4x1 high definition montage. Now, they're both nominally targeting the motor strip. Then when we predict the current flow pattern through the head produced by these two approaches, and so these black lines kind of show you that they're called flux lines. They give you the general sense of where the current is flowing. It is flowing from the anode to the cathode all the way through, right? It doesn't disappear in the middle. It must pass through. And then the false color at the level of the brain shows you where the current is going. So you can see that with the classical M1 SO tDCS pad montage, you're producing a current flow pattern that's through a good bit of the brain. And it's certainly not just under one electrode. It's certainly not under just the active electrode, as people might refer to the M1 electrode. And you can also see that the electric field is very clustered and it's kind of spread out all over the place. And so what you're seeing with the M1 SO montage is something that you'll see generally when you're doing pad-based tDCS or tDCS with large electrodes. And so I think when you're doing pad-based tDCS, there's a lot of nuance to where you place the pads. But because the current flow is so diffuse, you might often be thinking about circuit therapeutics as really underlying what's going on. Now, with high definition tDCS, I think you can see qualitatively just there's a categorically different pattern of current flow. With high definition tDCS, you can be non-invasive and focal with electrical stimulation. This is an idea that was first introduced with computational models. It was an idea that was made possible with MRI-derived models because you needed that level of detail to make these kind of predictions. But these models have since been validated. So these are really the two classes of stimulation that I want to talk about. Now, obviously, these are just models, and especially when they were first being developed, people would say, how do you know they could be right? We cannot know they're right without validating them. These models now have been validated extensively. There's probably 24 different publications that have independently validated the accuracy of these models. This is just one of them, which involved intracranial recording in subjects. These were subjects who had epilepsy, so they were undergoing intracranial recording as part of a mapping, preoperative mapping. But we took advantage of that in order to actually use those electrodes implanted in their head to measure the current flow as it flows through their head. And we had individual models of each subject with the individualized electrode placement. And I refer you to the paper for all the details, but the short of it is that the models and the predicted models and the recordings from these subjects, again, validated that these models are accurate. They're accurate if you follow a certain workflow, and that workflow does require you to use MRI specific, so gyroid precise, as we call them, models. Okay, so getting into really the targeting of high definition tDCS, though a lot of what I'm going to be telling you is equally relevant for regular tDCS. I wanted to talk about 4 types of approaches that we think about as ways you can optimize things. And I'll go through each one in turn. From the first 2 are really about what I would call anatomical optimization. And the last 2 get more into functional type of optimization. So as far as the first one of targeting optimization, well, it turns out that you don't just have to, instead of just moving the pads around, to different parts of the head and maybe running a simulation like this or running a simulation like that, or even running a trial with different kind of montages and seeing what happens. There is an algorithm that allows you to select a brain region that you're interested in, and subject to certain constraints, the algorithm will tell you how many electrodes you should use, where you should put those electrodes, and how much current you should put into each one of those. And so this is the publication cited here is the publication that developed the algorithm. It's since been implemented in different both free and commercial software packages. There are constraints. Always there's constraints, so there's no magic bullet. You cannot stimulate one brain region and have 0 everywhere else. And so These good software packages will typically allow you to specify the kind of constraints that you're interested in. These software packages may work with a generic head model. For example, we have something we call the New York head, my head, other heads that are provided as standards, or the software can load in a individual MRI and ideally process that MRI automatically. And I should say that the same software really that we traditionally developed thinking about transcranial direct current stimulation is really valid to a broad range of waveforms. So alternating current stimulation, even electroconvulsive therapy, even interferential stimulation. Sorry if you're hearing a little bit of background, I do have my kids at home today. And by the way, the same algorithm that was described in this 2011 paper can directly be extended to things like multi-target stimulation, deep stimulation. So we're really happy with this effort from 2011 because it provided a framework that was very generalizable and we think very robust. And so going from this automatic optimization based on target selection, another approach to optimization and target selection is closed-loop EEG. Now, this idea has been around actually for a long time. People will refer to it as reciprocity. The notion is that the brain is electrical and it generates electrical activity that you can pick up on the surface of the scalp. And then you will record that activity and then you will somehow invert it. And now you will use those same electrodes to apply stimulation and you will deliver the current to the same brain regions that generated the EEG. So some brain regions are, and that's illustrated here in this cartoon. So some brain regions are active. Why are they active? Because the person is undergoing a task. We're flashing a light or something. We're doing something to the brain is active. It generates the EEG that's picked up by the receiver. Then an algorithm, some software processes that and then makes a recommendation of how we should apply HD stimulation to get back to the same region. Now, the idea of reciprocity itself is actually decades old. I think what we contributed is we provided a closed form solution, so an automatic and optimized way to address reciprocity. The catch with our formula was that you did need the individual MRI. So we said that there's a closed form solution to this problem, a turnkey solution if you want, but to do this reliably, you do need the individual's MRI. But that collection of MRI and the segmentation of that MRI automatically was already part of the existing profile. So as far as anatomical targeting, I could say you can pick a brain region or don't, right? Don't pick a brain region. You can use EEG based. And in either case, there is software, I should say really algorithms that allow you to then optimize current flow to that region. And those algorithms are summarized in the papers below. And these algorithms have been implemented, as I mentioned, in a range of software packages. Some of them require more complicated engineering software packages. Some have been packaged into GUIs that are very accessible, could be used by a clinician. And some are somewhere in between, including open source packages. So this is one of the open source packages we've developed to make this kind of modeling available to everyone. It was named by a student. It's called ROAST. It's free in the sense that you do need to use it on MATLAB. It is open source and it's actually building on a lot of prior software that has been developed. And we're constantly, of course, updating it. So constantly working to make sure that this open source software has as many of the features as the most advanced commercial grade software available. Okay, so moving on, I want to talk a little bit about, so everything I've talked about now really involved maybe being as ambitious as picking a gyri and trying to focus into that gyri. But I want to talk about something I'm sort of calling it sub-gyri targeting. It talks about going sort of inside the gyri and thinking about the actual individual pathways inside the gyri. So as a quick reminder, here's in the top left, you see the cartoon of the anode and the cathode electrode on top of the head. And there you see current flowing into that blue arch is the cortex. And you can see that current will flow into the cortex, cross across the cortex, and then exit the cortex, right? It has to complete the loop. And here you have some histology that will be very familiar to people in brain research. You have these neurons. These are cortical neurons. And they are, first of all, oriented in a particular way. You see they're oriented, in this case, towards the surface. Their long axis is towards the surface of the head. And you can see that they're asymmetric. So the bigger bulb is the soma, and they have a longer dendrite pointed towards the surface, the apical dendrite, and a smaller dendrite pointed the other way. And these will sometimes be referred to as pyramidal neurons as well. And now we're thinking about this neuronal morphology in the context of direct current. So under the anode, current is flowing, if you will, down, so along the axis of these neurons this way. And under the cathode, so in another part of the brain, the current is flowing in the opposite direction, so it's flowing up the opposite way. And in between, right in this, what's in the orange region, the current is flowing sideways. And so for a long time, we've understood that these current flow patterns produce a resulting membrane polarization. It polarizes the membranes of these neurons in a very characteristic way that depends both on direction and on the angle. So you can see that the anodal direction here will be predicted, is expected, I would even say is known to depolarize the soma as well as the basal dendrite, while hyperpolarizing the apical dendrite. That's current going this way. But if the current goes the opposite way, you can see that the polarization profile also flips. So now the soma is being hyperpolarized and the dendrite is being depolarized. And when current goes sideways, we've known for a long time that this is not an effective way to polarize these neurons. The current is not traveling along their long axis. Now, taking it a step further, there's other structures in the cortex, and now I've added in these axons. Let's say these are afferent axons, let's say from one cortical region to another cortical region. And let's say in this cartoon, they're oriented this way, right? So these are, we might call them tangentially oriented. In this situation, these tangentially oriented axons are not polarized in the anodal or cathodal direction, because the anodal and the cathodal direction is not along them. But in this tangential direction, this sideways direction that is not effective in polarizing the neuron, we do polarize the terminals. Okay, so this is a lot of cartoons, and I've cited some papers below that are from BrainSlice. This is what the BrainSlice looks like. So it's a tool that I've been using in my lab for, I guess, a long time now, and it allows you to characterize. It allows you, first of all, to apply both anodal and cathodal stimulation. There's no skull; we can't really call it transcranial, but we can apply current in a very specific way relative to the structures. Again, sorry if you're hearing the kids in the background, but they got school too. We can, in a slice, in a way that is certainly not possible to do in people and is very hard to do in vivo in animals, we can record and probe the brain slice in a very nuanced way. And so the brain slice has allowed us to gain insights into the effects of tDCS. This is one paper from 2004. This was actually back when I was a postdoc in the UK. And in this paper, there's the brain slice applying direct current across the brain slice. And a key aspect of this brain slice preparation is we were able to probe the excitability, the function of distinct pathways. And so those are labeled here as LM and OR. LM and OR are two different axonal pathways that are synapsing onto the same cell. So the target is the same. It's that cartoonish pyramidal neuron that's illustrated here, but there's two separate pathways going on. And what we can do in the system is we can probe the efficacy of this pathway and probe the efficacy of that pathway. And why that matters, I'll show you in a second. And also, it's very easy to brain slice to control direction. So now in this cartoon, anode is on top, cathode is on the bottom, or we can also do anode on the bottom, cathode on top, so that current will go this way, or we can actually rotate the wires, or what we actually do is we rotate the slice. And so now we can produce current in the sideways direction, right? In the sideways direction. And so this paper unpack these in a lot of detail. I just want to give you the highlights. So this is, first of all, for the OR probed pathway. And the basic experiment is we probe the system. That's the control situation here. And you see a stimulation artifact, and then you see a blip. And that blip is generally a measure of the excitability of that pathway to a test pulse. Now we turn on the field. The field in this case is only applied for a second. And while the field is on, we test the pulse again. We test the pathway again. We get another size response. Then we turn off the field, and then there's a control post afterward to see if the excitability of the pathway recovered. And what you can see in this case is that the 40 millivolt per millimeter condition caused the evoked response to get smaller, effectively saying that that pathway was less excitable, while the minus 40 millivolt per millimeter field made the response bigger, so making the pathway more excitable. And that's unpacked in a lot of detail in this paper. It's also shown in the figure below, where you can see that as the applied field increases in amplitude, the modulation of the evoked response gets bigger and bigger. And also there's an effect on timing. So the bigger it gets, the faster the peak arrives and it recovers afterward. So what this showed is that if you have a system that is active and you put a direct current stimulation on top of it, you can modulate the excitability of that system. And this is of a particular pathway. And the reason I explained this in some detail is I now wanted to contrast that with what we found when we probed a different pathway. So this is the LM pathway. I should mention everything I'm showing you here is in the hippocampus. When we went to the LM pathway and we applied the anodal and cathodal variant of fields, I should say the negative numbers are the anodal variant and the positive numbers are the cathodal variant. So this is a convention that we started here that's since been followed, where when you see negative electric field, think anode and anodal, and when you see positive electric field, think cathodal. When we went to the LM pathway, we saw a very different behavior. Essentially what we saw was both anodal and the cathodal variant made the response bigger, but they made it in a bigger and a slightly nuanced way and slightly different way. As you see the different rows in the LM probe pathway figure, you can see that the control response is getting bigger. What that means is that we're probing the system more and more intensely, weakly, more intensely, maximally intensely. And you can see in the final row, we're actually producing a maximal response under control conditions. That means that without a direct current field, without applying any direct current, the response is already maximal. In this situation, this is the bottom row of LM, when we applied 60 millivolts per millimeter, the cathodal variant, the response didn't get any smaller. It was so intense that the direct current stimulation couldn't make that response any smaller. On the anodal side, it would appear that the response got smaller. So this is the maximum control response with minus 60 millivolt per millimeter. And it would seem the response gets smaller, but what actually is happening, what's showing in that arrow, is we're actually producing this double response. We're kind of recruiting the population in two different ways. And all that is unpacked in a lot of detail in this paper. This discovery actually took years to unpack. The point I want to give you is that different pathways are influenced differently by direct current stimulation. We like to say anodal is up and cathodal is down. We know it's much more complicated than that. And even very early on here, right, in 2004, 2003, it was becoming aware that even what anodal did or what cathodal did would depend entirely on the nature of the activity of the probe pathway and what that pathway was doing. And by the way, in the same paper, we also looked at the sideways direction of current flow and found that it was effective. And we unpacked why it is. Okay, so we can skip forward over a decade to some work done in John Rothwell's lab, led by Richie Hanna and others. And now we're going back to the human situation. We're back to transcranial stimulation. And in this particular experiment, which I'll just walk you through really quickly, bipolar HD tDCS was applied, meaning there were just two, there were small electrodes, there were high definition electrodes, but there were just two of them. One was always the anode and one was always the cathode. And they were oriented one of two ways. They could either be oriented in a way so that the current sort of flowed along the motor strip, or they could be oriented in an orthogonal direction where current was sort of slamming across the motor strip. And in the first case, where it's kind of flowing along the motor strip, you wouldn't predict the current to flow along the way that would polarize the long axis of these pyramidal neurons. They're kind of flowing along them. Well, in the other case, when you're kind of slamming across the wall, that's when you would predict that the current is entering the gyroid wall and really flowing in a preferential direction along these pyramidal neurons, producing maximum polarization. The intensity in the motor strip, or specifically the hand knob in each case, is matched. So you don't, the total amount of juice flowing is the same. The difference with these two conditions is the direction of the current flow through the motor strip. So we're looking at directionality. What Ritchie and Rothwell and others did in a series of experiments that spanned both using probing brain excitability and going all the way to behavior, is they found out that this direction really mattered, that it's not about how much intensity you deliver to a brain region, but just rotating the electrodes and delivering the same intensity produced completely different outcomes. And what made it still more nuanced is the way they were probing the system was they were using TMS, which I think this audience is very familiar with. They were using TMS to produce a finger twitch and asking how does tDCS on top of the TMS modulate that finger twitch. And what they found was there's a complicated interaction. What the tDCS did depended on the angle of the tDCS, but also on the angle of the TMS. Now, when you're changing the position of the TMS, what you're doing is you're activating different pathways. You're probing different pathways. TMS pointed this way will preferentially activate some axons. When you rotate the TMS, the idea is you're going to preferentially activate a different set of axons. And lo and behold, depending on which axon pathway you were activating, the same direct current had different outcomes. Okay, and I'm also presenting this, I'm framing this in the context of the work we're doing in Brain Slice, because they really are telling the same story. What direct current stimulation does depends on the pathway. And two different pathways arriving in the exact same region may be modulated in a categorically different way. And I don't think this is a problem. I think this is an opportunity, provided one knows how to leverage it. And there's a lot more work on this type of pathway specificity, but I just wanted to present the idea here, and then maybe get into the final point of how targeting may be achieved. So this is functional targeting, something we call functional targeting, and I deliberately contrast that to anatomical targeting, which is really what the first 2 points were about. So taking a step back, many forms of neuromodulation, most forms of neuromodulation are suprathreshold. So transcranial electrical stimulation with a big T that produces a motor twitch. Transcranial magnetic stimulation is suprathreshold, produces a motor twitch. Electroconvulsive therapy is certainly suprathreshold. And so what you're having in these situations is that the electrode or coil is placed on the scalp. It produces a current flow in a particular brain region, and it makes those neurons fire. If it's pulsed once, the neurons fire once. If it's pulsed twice, they fire twice. If it's pulsed at 100 hertz, they fire at 100 hertz. And so suprathreshold stimulation is always about pacing. And if it appears to produce an inhibitory effect in some sense, the inhibitory effect must be somehow secondary to the pacing, but it always starts with firing. Now, subthreshold stimulation is a bit different. And so we're thinking about transcranial direct current stimulation, but also transcranial alternating current stimulation, tACS, and also transcranial random noise stimulation, tRNS, and other variants. These are low intensity. So I should say whether in these cases ECT or tES with a capital T might use 1,000 milliamps. Now we're back to 1 milliamp, 2 milliamp. And so in this situation, there is still a current flow through a brain region, but it is much too low intensity to produce firing, right? And so these neurons that were not firing are not going to be made to fire. So typically that's what would be called subthreshold. And so there's no de novo firing. If you're inactive, you're going to stay inactive. However, we know that the brain is never inactive. The brain is constantly active. It's active even when you're watching this talk. It's active when you're at rest. And it's certainly active when we're asking people to engage in a task, like practice this motor task. Think about this. Cognitive behavioral therapy, rehabilitation, all these things will activate the brain in a specific way, but anyway, in any case, it's active always in any case. And so now when we think about subthreshold stimulation, what we're thinking about is you're passing current through a brain region, and that brain region includes neurons that are both already active and neurons that are inactive, and only those neurons that are already active will get the benefit of the stimulation. So again, the current might be rather diffuse, and it might be influencing many different types of neurons, but if some of those neurons are very, very quiet, and if some of those neurons are very, very active, only the active neurons will be modulated, will draw the benefit of transcranial direct current stimulation. And again, this is distinct from anatomical targeting. Theoretically, you could be passing current to the entire brain, but only influencing those networks that are active. So this is this notion of functional targeting. And on the one hand, it's presented as a novel idea or a new way to think about it. On the other hand, if you look at the history of transcranial direct current stimulation, going back to animal work, not just in 2003, 2004, but in the 1960s, in a sense, it was all functional targeting, meaning it was always the sense that you were modulating pathways that were already active, not generating de novo activity. So I want to show you some data again from a brain slice to unpack this idea in a little bit more detail. Again, looking at the anodal and cathodal variants. Now, there's two aspects to this experiment. Let me walk through each one in turn. The first one here has nothing to do with direct current stimulation. What we're doing is we're using theta burst stimulation. We're using the same electrode that we're using to probe the system. We're using it to apply this burst of stimulation. And this burst of stimulation produces a lasting change in excitability. So it'd be called long-term potentiation. And that lasting change in excitability is measured as an increase in the excitatory postsynaptic potential, or EPSP. So we probe the system, we have the initial EPSP, we blast the system, and then we probe the system again. And it's well known that done correctly, this type of intervention will produce a lasting plastic increase in the EPSP size. That's the first part of the experiment. The second part of the experiment is at the same time as we're doing this burst stimulation, we apply either the anodal or the cathodal form of stimulation. We're not asking whether anodal or cathodal stimulation generates plasticity. They don't actually. They don't on their own generate plasticity. We're wondering whether they will modulate plasticity. So this is the result of one of those experiments. This is again in a brain slice. We have an electrode that is used to both probe the excitability of a given pathway and energize it during the theta burst induction. There you see the pattern of theta burst stimulation at the top, tDCS. So it's applied in a very particular pattern for a short period of time. It just takes, I think, 3 seconds. It could be applied on its own without direct current stimulation, or it could be applied with anodal direct current stimulation or with cathodal direct current stimulation. And then the figure there shows you the main result. So before theta burst stimulation or direct current stimulation, which is the period before time is equal to 20 minutes, we have a stable baseline. 1 means we've normalized the pathway excitability, this EPSP, or I should say field EPSP as we're recording it, but we've normalized it in the period before 20 minutes. So you see that before 20 minutes, things are stable. Then at t is equal to 20 minutes, the theta burst stimulation is applied. That's the black dots. The excitability goes up and it stays up, right? So the theta burst is over, but with some diminution, you can see that for the course of this experiment, so out towards 80 minutes, the excitability remains elevated. Now we can repeat the theta burst stimulation with anodal, which is in this case pink, and you can see that the theta burst stimulation now produces more plasticity. So the same theta burst, the same plasticity induction protocol, combined with the anodal version of direct current stimulation, gives you more plasticity, more bang for the buck. You can see that on the side as well, that in the plus 20 volt per meter case, you got more plasticity. And I should mention for this particular experiment, in this case, the plus represents the anodal form, and that has to do with the convention of how these neurons are oriented. But in this case, the plus represents the anodal variant. It is making the response bigger, and the negative represents the cathodal variant, and it is making the response smaller. It's not shown in this trace, but if we apply, as I mentioned before, if we apply the direct current stimulation on its own, we will not produce plasticity. In our hands, direct current stimulation on its own, even at very high intensity, even for very long duration, does not produce significant plasticity. So what does this mean? It means that if a synapse is undergoing plasticity, it will get the benefit or the modulation of the direct current stimulation. If another synapse is not undergoing plasticity, it's not going to be activated by the direct current stimulation on its own. So this is functional targeting. It's been shown in many publications. This is a recent one where we describe this form of functional targeting as really Hebbian and leveraging Hebbian plasticity. And in interest of time, I'll skip some of these points, but Hebbian plasticity is known to follow certain rules. This includes rules like associativity, and we show that when tDCS boosts plasticity, it respects all those Hebbian rules. And so as my colleague Lucas Parr says, he sometimes says tDCS is Heb. And so this is an example, for example, from this paper where there are two pathways being probed. You can think of one as the one is strongly activated, one is weakly activated, and the point is that the weakly activated one wouldn't experience plasticity on its own, and because it wouldn't produce plasticity on its own, it wouldn't get the benefit of direct current stimulation on its own. But the strong and the weak are activated at the same time. The strong one does get the benefit of plasticity, and then it transfers some of that plasticity to the weakly activated pathway. So this is associativity, and it's something that can be demonstrated very robustly in a slice. And for people who work on behavior in people, there's an inference there as well about how plasticity boosted by tDCS might actually generalize. But all of it still falls under the rubric of this notion of functional targeting. We're not talking about where the current is flowing. The current could be flowing everywhere at once. We're asking really about which pathways are activated and about those pathways getting the benefit of stimulation. Okay.
Marom,
yes.
You've got a question that related to the slide you just showed. Directly.
Yes.
Will it be apt to say that tDCS will result in an enhancement in behavioral function when the neurons are sub-maximally utilized? On the other hand, if the neurons are maximally utilized, tDCS fails to show any change in behavior as there is no room for improvement.
Yeah, and so obviously, we always want to be careful when drawing inferences from slices or animals to people, and so we're talking about LTP versus learning, but obviously I've been blurring that distinction. Maybe one way to answer that is this: not shown here is there's another experiment where what we do is we apply the theta burst once and we produce plasticity. We apply the theta burst again and we produce more plasticity. But after a while, we can't produce any more plasticity in the slice. That slice is maxed out. So there's a ceiling level of plasticity. Now we repeat that experiment with the nodal version of direct current stimulation. The first blast of LTP combined with the nodal, you get more benefit. The second blast, you get more benefit. And what we find is actually that plateau, the maximum amount of plasticity, learning that brain slice can undergo is actually higher with direct current stimulation. So direct current stimulation doesn't just give you more bang for the buck on that initial plasticity induction, doesn't just make you learn faster. It also raises the ceiling for learning. So maybe in response to that question, it may be the case that we're applying tDCS with learning, and we can make that learning better. But if that learning has reached a plateau where the training just can't get that person to the next level, tDCS might allow you to get to the next level. So might actually increase the top end of how much learning is possible. I've done a lot of loosey-goosey moving between brain slice and people, and I hopefully I addressed that question. So meaning tDCS can boost what the max even means.
Okay, brilliant.
That being said, we do have experiments where a very, very active system, when you apply the nodal version of tDCS, it ends up being suppressed. And so I'm presenting here, I should emphasize this, I'm presenting here a very simple picture where nodal tends to go up and cathode tends to go down. But I did show earlier hints where that's not always the case. And that's certainly the case with LTP as well. So depending on the nature of the plasticity that's ongoing, a nodal can push it down or cathodal can push it up. These are things that we've unpacked in specific publications in Brain Slice. And so I guess the other answer I could give to that is there could be a situation where you have so much ongoing plasticity, beneficial, let's say, and you apply direct current stimulation, and maybe that has a destructive role on it. We see cases of that in the slice as well, where now you have, so then you're actually making things worse.
Okay.
So I've talked about different forms of optimization. Though I talked about them in the context of high definition tDCS, they all apply to regular tDCS. So in the context of these optimization algorithms, I mentioned where you can pick a brain region and ask the software to prescribe a ideal montage. You can say, I'm only going to use 2 electrodes. So give me the ideal way to place these 2 electrodes. So anatomical targeting can still be done with regular pads using the exact same algorithms because the algorithms have the constraints built into them. And same thing with the EEG closed loop. You can do it, but obviously with high definition, you have more nuance. The sub-gyri targeting, the functional targeting, these things again should apply equally well to high definition versus regular tDCS. And so I think that with high definition tDCS, you just have more degrees of freedom. Right. And so by nature, you're going to have more flexibility. You're always sort of going to win in the ultimate targeting game or in the capability game, just because you have more cogs that you can play with than with regular tDCS. And that was sort of the rationale for the development of high definition tDCS to begin with. And if your goal is really to just deliver current to just one brain region and not deliver current to any other brain region, high definition is going to be a superior tool. But with conventional tDCS, we have a rich literature showing dose response, montage specific effects, and very compelling, though still investigated, behavioral and clinical outcomes. And so we have a tremendous weight of good science to lean on when we're talking about regular tDCS, and regular tDCS is just more deployable. And so this is really the last slide I wanted to have to bring it back to this point of the times that we live in. tDCS can be done at home, but it's really conventional tDCS that we think can be done reproducibly and easy at home. When you go home with neuromodulation, including tDCS, I don't think it's everything goes. I think you still need to follow strict rubrics and strict protocols, the goal of which is to make sure that when someone gets tDCS at home, they're getting the same kind of tDCS they would be if they were at the clinic or the medical center. And so it's really governed all by reproducibility. We want tDCS at home to be reproducible, to reproduce what's done at the center. And if it reproduces that, we expect that its outcomes and its tolerability would always be the same. And so we and others have worked very hard on developing these rubrics. We call them remote supervised rubrics. They were recently summarized in 2020, both thinking about research and clinical practice. This was actually right before COVID hit, but more recently in a large consensus document that addresses neuromodulation in time of COVID, remote tDCS really stood out. The remote tDCS trials are in many cases hardly even slowed down. In some cases, they are ramping up in the current period. But I think obviously home-based tDCS, home-based neuromodulation in general has tremendous promise, especially for patients who have a hard time getting around as it is. And in some sense, the situation we're in right now is just giving that a little bit of a kick to accelerate that deployment of it. And I wanted to stop there and thank everyone for, again, the attention and Brainbox for the opportunity. And if there's time for more questions, I'm happy to take them.
Great. Thank you for that, Marom.
Should I leave my screen on the way it is or?
Pardon?
Should I stop sharing my screen or just leave it the way it is?
We can leave it on this for now, and I'll read out the questions. That's okay. So we've got quite a few. So amazing talk. Thank you. My question: applicability of high definition tES in terms of time and comfort, i.e., EEG electrodes placement, time for clean recordings, etc., for patients with motor disorders and chronic pain, for example. So I think they're asking how feasible it is to get all the EEG kits set up and get clean recordings in a patient population, and how feasible that is.
In my opinion, very feasible. I think companies like Rogue and other companies have provided great solutions that combine transcranial electrical stimulation with EEG. There's just a really nice inherent form factor. High definition are small gel-filled cups. EEG are small gel-filled cups. Now, they're not the same gel-filled cups, but they're both little gel-filled cups. So I think as far as mechanical integration, there are many great solutions out there. In some cases, what you're doing is you're losing some EEG positions and you're giving them up for stimulation positions. And there's other solutions as well. But on the mechanical level, I think it's very well done. If you're from a we do this in my lab the whole time. From a technical perspective, you're essentially filling the EEG electrodes the same way you're filling the stimulation electrodes. I think, and so I don't see any issues with comfort or time. I would caution though about electrical interference. Now, you can record prior to stimulation, then you can stimulate, and you can record after, and then you don't have to worry about artifacts. It's a very clean, it's a very nice experiment. Many people want to record while they stimulate. And at least in my own lab, when we've dug into this in detail, we found that there are very severe and hard to extract artifacts. So I would say that part of it, not the mechanical integration, but the online electrical integration, I think that needs some work. I think it's tractable, but that needs more work.
Great stuff. Thank you. Second question is, how could we know that the area detected as active by EEG to be then targeted by tES is excitatory rather than an inhibitory node in a specific task?
Oh, that's a great question. That's a great question. I don't have a good answer. It's a very good question. I think one thing I would say is, generally speaking, the notion that, anodal winds the brain up and cathodal winds the brain down, that notion is strongly based in some classical work by Nietzsche and Paulus and others showing how the TMS MEP is modulated. But those same authors have shown that it's really much more complicated. For example, cathodal at 2 milliamp is excitatory on that measure. If you prime the motor region, so have the person flex their wrist and apply a nodal, the anodal now produces a decrease, suggesting that if the system is active during a nodal, there's a decrease in excitability. I think the better answer is that when we're talking about increases in excitability, decreases in excitability, that is always sort of a gross oversimplification of how the brain works. It's convenient, but it's had its own limitations. And if anything, the work combining tDCS and TMS has stood out for showing how things are much more nuanced than that. And so I'm dancing around the question in the sense that maybe one thing we can do is we can move a little bit away from this notion of always thinking about, do we need to wind up or do we need to wind down the brain, and rather think, look, we're applying current interbrain region, we're washing that brain region in current, and we will modulate it. One thing I didn't talk about, but it was in the slides here, is that we and others have found that a nodal boost of plasticity is much stronger than the cathodal inhibition. And this has been true across different models of plasticity, meaning it's, for some reason, it's easier to boost plasticity than to suppress it. And again, this supports the notion that if we can wash the brain in current, without the ability to necessarily control directionality with a lot of nuance, we might still produce a net up in terms of plasticity, a net benefit. However, that still doesn't answer the underlying question, which is the point that, if you're recording the EEG and you're identifying your brain region of interest, will the algorithm that we develop tell you whether you should excite it or inhibit it? I guess the short answer to it is no. The algorithm would identify that brain region, whether that signal, your desire is to boost that signal or inhibit that signal, or for generally boost the activity or decrease the activity in that brain region. I guess that would be based on some sort of a priori information. So that, yeah, the algorithm does not provide that answer.
Great stuff. Thank you. They got a good question here. Hang on, let me just find it because they are rolling in at quite the pace. Naive question. Have there been any studies comparing the effects of conventional tDCS to the effects of tDCS? Doesn't the fact that conventional tDCS induces a current over larger connected regions in the case of an M1 supraorbital montage cause a different effect than a more localized stimulation as in the tDCS montage?
Right. So comparison of conventional versus high definition. There have been a few, let's call them head-to-head comparisons, including by Michael Nietzsche himself. So Michael Nietzsche did a crossover study in a group of subjects where they received M1 SO stimulation. I think it was crossover, but it was within one study. Some subjects received M1 SO stimulation. Some received the 4x1. There was either the anode or the cathode over the motor in either case, and he asked what happened. What he found was that that high definition compared to conventional tDCS produced a different time course of after effects and an also different magnitude of after effects. In that particular case, conventional tDCS had a larger immediate after effect, and then the high definition after effects sort of increased over the course of 30 minutes and eventually became larger than the conventional effect had ever been. And in that particular study, this was 10 minutes of stimulation. I believe it was after an hour, the effects of conventional tDCS had faded out. They were no longer significant, while the effects of high definition tDCS were still significant an hour later. And there have been other direct comparisons. When I look at studies like that, I tend to interpret the conventional in terms of the high definition instead of the high definition in terms of the conventional, if that makes sense, right? So the conventional is stimulating many parts of the brain, including, let's say in this case, the motor cortex. And the result you see is the result of stimulating all those brain regions together, while with high definition, you're stimulating just one brain region. And so for me, that's almost conceptually like a cleaner experiment to interpret. And so, for example, if a pad montage were to have an effect, and then the high definition montage would not have an effect, the way I would interpret that is that the pad isn't stimulating the region you think it's stimulating, right? It's stimulating other brain regions or a cluster of other brain regions. And so again, when a lot of these head-to-head comparisons, for me, the question really isn't at this point which one is better. I think we're far away from that. The question is really when you do these two things at the same time, I think these experiments can teach us a lot. Whether one works better than the other isn't sort of like the most interesting thing. It's just asking why did one work in one case and did one not work in the other. Generally speaking, obviously there's been also clinical work on high definition tDCS and conventional tDCS. And I think the jury is out of which one produces better clinical outcomes. Like if you're going to use one for pain versus the other one for pain, migraine, let's say, which one works better, which one works worse? I think the jury is still out, partially because the jury on efficacy and optimization on either one is still out. So when we're still optimizing both approaches, we're not at the point yet where we should be, pitting them up against one another. I think really the pitting up against one another is more interesting, I think, from a scientific and research perspective at this point.
Brilliant. Thank you so much for that answer. Are you still happy to take more questions?
Absolutely, yeah. I appreciate them, but these are all really, I'm not saying it, these are all really good questions. I do appreciate them.
No, I think they're brilliant too. So this is going back to the idea about raising thresholds and so on. We spoke a bit about it with the Hebbian stuff on this slide I'm showing now. It came up then. I have a question regarding the functional targeting and sub-threshold modulation of tES. Specifically, are the high frequencies of alternating currents more than 100 Hertz filtered by neuronal membrane? It is described sometimes as a low-pass filter. If so, how can we explain the high-frequency tACS or tRNS effects?
Right. So if I understand that question, it's not necessarily talking about the theta burst.
No.
but generally about using, let's say, transcranial alternating current stimulation with 100 hertz, 200 hertz, 1 kilohertz, and so on. So I don't have that data here, but in these same brain slice experiments, one of the things we can do is we can record from inside a cell, and we can apply fields, and we can ask, does the cell filter those fields? And what we find is that the cell does act like a low pass filter. What that means is that neuron polarization doesn't like things that change fast. They don't respond well to things that change fast. So we can see that from the step response to a square wave, but we can also see that as we apply different sinusoids. And so as you're applying sinusoidal stimulation from going from DC, 1 hertz, 100 hertz, 60 hertz, by the time you're getting to 100 hertz, 200 hertz, you're seeing a severe penalty. The response gets weaker and weaker. And by the time you get to 1 kilohertz, the response is still weaker still. Now, it doesn't mean that there's no response at all, right? It means that the response is just getting weaker and weaker. And so if you want to produce the same amount of membrane polarization, you now need more juice. So for example, if you're doing 1 kilohertz stimulation, you might need 500 milliamps to produce the same polarization as 1 milliamp with tDCS. So a priori, that would suggest that as you go to higher and higher frequencies, you're going to lose potency. But the brain is complicated. The brain is not linear. So for example, one thing the brain has is it has it can have phenomena that almost look like resonance, where sometimes you apply a certain frequency and the brain responds very robustly to that frequency. A great example would be oscillation. So we and others have shown if the brain is oscillating at a certain frequency, let's say it's oscillating at 50 hertz, and you, hi Rafa, this is not a good time. So that was my son, but anyways, if the brain is oscillating at 50 hertz and let's say there's a 50 hertz oscillation and you apply 50 hertz stimulation, that 50 hertz stimulation is very effective in modulating the 50 hertz oscillation. So there are certain situations where there could be a sweet spot for certain frequencies to engage with some sort of inherent nonlinear process, some sort of resonance phenomenon at the single cell or at the network level. Those kind of phenomenon, though, tend not to exist at that high hundreds of hertz, kilohertz range. And so if the question really is, why would 1 kilohertz work at low intensity? I think that is an open and interesting question where we still haven't discovered, in my opinion, we still have not discovered phenomenon at the brain where at that 1 kilohertz, hundreds of hertz range, there's some kind of resonance, some sort of magical boost in sensitivity.
Yeah. Thinking of that.
I hope I answered that.
They are questions following in. Hang on, I'm just going to go back. So earlier on, you spoke about anodal tDCS and like a plateau, and anodal can like push up that plateau and that ceiling and so on. And that this question came in whilst you were discussing that. Why not use tRNS to prevent reaching a plateau? Is there any study showing the mechanisms of tRNS? I think you kind of touched upon that in the previous one.
I did, but I'm actually really happy for that question because I omitted something. Yeah. I think when I was talking about the higher frequency. There's some really interesting work, for example, from several groups, but including from Dominique Durand and William Stacy, who was a colleague of mine at the time when I was at Case Western, where they looked at something called stochastic resonance. And stochastic resonance basically says that if you have a system and you start injecting noise into that system, you can start to make that system, you can increase the excitability of that system and actually make it more sensitive to detecting an input. So you have an input that would normally come in and that system simply wouldn't detect it, but now you're injecting noise and that same input comes in and you're able to detect it. So that's this notion of stochastic resonance. Now, too much is not a good thing though. If you inject too much noise, you overwhelm the system. So there's a sweet spot of noise that you're injecting where you're injecting enough noise to increase sensitivity to an input, but not so much noise that you're completely washed out the system. And stochastic resonance type phenomenon have used random noise stimulation They have used very high frequency stimulation. And so that may be actually one very interesting and biophysically supported area where high frequencies and random noise may do something that I'm aware of. There may be others as well.
Nice one. Thank you. Next question. Are there any clinical applications for tDCS now?
Are there any, sorry?
Are there any clinical applications for tDCS now?
Clinical applications. You know, the regulatory status of tDCS varies from region to region. In Europe, tDCS is cleared, has a CE mark for a range of indications: depression, pain, I believe stroke rehabilitation as well. In much of the rest of the world, tDCS has been approved by whatever regional body it is for different indications. The US is traditionally very slow in approvals, and so in the United States, transcranial direct current stimulation is not FDA cleared or FDA approved for any indication currently. So that's on the regulatory answer. You know, on the weight of the clinical evidence, I think that there are certain indications, such as, for example, depression stands out, where you can point to, you know, controlled, large, pivotal trials that produce very encouraging results. So and I'm trying to be very diplomatic in my answer here. I don't want to promote, you know, tDCS for any particular indication and get ahead of the literature, but I think everyone on this call knows there's been a lot of clinical investigation of tDCS, and the technique has shown a lot of promise, especially in patients who, you know, are refractory to drugs. They've failed everything else. So these are very difficult patients to treat to begin with. They're at the end of the line. And so I think we can agree that there's at least encouraging signal. We can also say that as far as the side effects, tDCS is very mild. Whenever you're thinking about deploying something to a patient, it's always about risk benefit. And the risk associated with tDCS currently is considered so low that we routinely try it on college kids, right? Just to see how it's going to change how they think or how they feel. And so when making a decision, which is ultimate medical decision about whether a patient should get tDCS or not, there's a lot of factors to consider, but obviously risk benefit is the ultimate one. And I think that's something that's often maybe not emphasized enough, that, you know, it could be, you know, that the worst that can happen with tDCS is, you know, you waste your time, right? You wasted your time when you could have been using your time to do something else because it was, but not that there was any sort of lasting injury.
Great stuff. Thank you very much. Sorry, I've got a bit of a problem with my battery charging on my laptop, so I was just seeing to that. Thank you so much. The next question. Are you still happy to take them? Still happy to take questions?
Please. Yeah, I really appreciate these.
Yeah. Great talk. Could applying tDCS in a more temporally specific manner, i.e. during specific movements during learning, boost Hebbian plasticity in a similar way to the theta burst stimulation in brain slices, given the fire together, wire together hypothesis?
So if I understand the question, it's really about timing. So in my own lab, we found that the best time to apply tDCS is during the plasticity induction. So meaning at the exact same time that the plasticity is happening because the person is practicing or training, in our hands seems to be the optimal time to apply transcranial direct current stimulation. In fact, I might even have a slide on this. Hold on. These are my bonus slides. Nope, I don't have a slide on this. What we were able to do in the slice, so in this experiment, the direct current stimulation is on the whole time as a theta burst. In the slice, we can be even more nuanced. We can turn on the direct current stimulation only when the theta burst is applied, like just for that few milliseconds. And again, what we find is the only thing that matters is that the direct current is present exactly at that moment that the theta burst pulses are applied. But generally speaking, in the work that we've done in Brain Slice, it's applying it at the same time that is the most effective. Whereas in Brain Slice in our hands, if you apply it before the plasticity induction or after the plasticity induction, we're not seeing any benefit or certainly as large of a benefit That being said, it's known that from the human research that in many cases, for example, in rehab, direct current stimulation will be applied before the rehab. So you have stroke, you're getting tDCS, so you'll sit down in the chair, you'll get tDCS first, and then you'll undergo your rehab, and that's been shown to be effective as well. And I don't think that necessarily is incompatible with what we're showing here for a variety of reasons. One is that whereas the brain slice is dead quiet unless we do something, the brain is never dead quiet. And so if you're doing tDCS to someone, whether or not you are actively telling them to engage in a task, their brain is very active. So you're already engaging an active system, and that priming could lead to some sort of after effects. And the second thing is, I think there's a lot of things in the brain that are not captured in the brain slice. One topic I'm very interested in is the vascular response to direct current stimulation. The most obvious thing when you do tDCS is skin redness, right? And it turns out that redness also happens at the level of the brain. And you can image that, for example, if you do fMRI after tDCS, you see an increase in bold response. But this new thinking says that actually, it's not that the direct current stimulation is activating the neurons and then through neurovascular coupling activating the blood supply, but that direct current stimulation can directly activate the blood vessels directly and essentially increase brain metabolic capacity, increase clearance mechanisms, and that this activation of blood flow might have a very different time course than direct neuronal activation, and will be able to support plasticity learning. And I think I wanted to insert that point, and so I don't know if that was directly relevant to answer this question, but I did want to mention this, that there's other neuronal targets, endothelial cells of the blood-brain barrier, glia, and so on, and when we're doing brain slice experiments, we're only capturing a very small subset of those in a very specific way. And so the time course insights we get from brain slices may therefore be limited, and there may be much more nuance when you're working with people. I'm not sure if I fully addressed that question. I hope I started to.
Right, okay. Good bump on my side. Next question. Please could you talk a bit about the non-linear effects of tDCS, i.e. current flowing into and then out of a structure will have both excitatory and inhibitory effects on cells oriented in different directions, but overall the direction of the effect won't be cancelled out.
Yeah, so, and that I do have an extra slide for, because I think it's a really interesting. What this shows is, what you don't see here is that there is a large anode over the motor region. And this is a prediction of the current flow through the brain during the M1 SO tDCS montage. And you're seeing, and then you can see here a zoom in of one particular gyri, and those arrows show you the direction of current flow. And you can see the current is flowing in through one side of the gyri and exiting on the other. Whether you're doing any form of conventional tDCS, whether you're doing any form of high definition tDCS, this is what we see. The physics of the current flow are such that typically it will enter on one side of the gyri and exit off the other side of the gyri. So in this case, we'd say that the right side of the gyri is getting anodal, and the left side of the gyri is getting cathodal. And there's no, we can control which side gets the anodal and which side gets the cathodal, but we can't make it go away. It's very hard to make a situation where the entire brain region that you're interested in has only inward anodal current flow or only outward or cathodal flow. So we're always dealing with this mixed bag. So is this a zero-sum game? So the answer is no for a couple of reasons. One is it's still the case that under the anode, and this was quantified in the paper that's referenced here, it's still the case that under the anode, there is more surface area with inward than there is surface area with outward. And under the cathode electrode, there is more brain surface area with current exiting than current entering. So it's not exactly even. Still, there's more, there's stuff going in and out. So we thought a lot about this. There's different ways to reconcile this. One is to make the argument that, for example, the inward counts and the outward doesn't. Right? So let's say inward boosts plasticity a lot, but outward cathodal doesn't inhibit plasticity very much, and we have data for that, right? That's not just speculation. We can unpack that. Sorry, I'm going through this very quickly, but we can unpack that in other ways. This is another paper where we looked at input-output functions, and I don't want to spend time to unpack this fully here, but I can refer to. But this paper once again showed that when you look at input-output, anode produced more bang for the buck than cathode, meaning a nodal polarization modified input-output. Cathode changed excitability, but it didn't modify input-output. And so what we produce is an image that looks something like this. I'll spend 30 seconds on this. Here's the gyri, and you have current flowing in, and you have current flowing out. In this case, you have the anodal. In this case, anodal is blue, and cathodal is red. And it could be that the anodal produces an effect, in this case on input-output, while the cathodal doesn't. And so if you look at the gyri as a whole, there is still a net effect. And so what I'm trying to say is that if you have current flowing in and out of the gyri, because the brain is highly nonlinear, it doesn't mean there's a zero-sum game, right? And by the way, we see this again with things like plasticity, input-output, oscillations. And often, I would say again and again, the anodal produces more of a boost than the cathodal produces an inhibition. So if you have an entire gyri that's oscillating, and one side gets anodal and one side gets cathodal, the whole gyri might oscillate more because the anodal has more of an effect. And this is something, again, this is something that I'm not just speculating on. This is something that we have unpacked in detail. I just had the slide, and this is, you can see here that we're looking at directionality, we're looking at network response. And so it's not a zero-sum game. And as I keep emphasizing, it seems to be, the bias seems to boost, not towards inhibition. I hope I started to answer that question, and I think these references get at it as well.
No, you said it, I think. Good. Quick one now. Please explain all of Hebbian plasticity.
Sure, please explain Hebbian plasticity. Was that the question?
That was it. Can you please explain on Hebbian plasticity again?
Yeah, I mean, the simplest rule for Hebbian plasticity we all know, right, is neurons that fire together wire together, right? And so it's an idea that has been unpacked a lot, for example, in brain slices, where there is thousands of papers on long-term plasticity in brain slices showing that when you have a presynaptic neuron that fires and when you have a prosynaptic neuron that fires, if they're both firing together, the strength between them will be strengthened. There's nuance to that, there's questions of timing and so on, but that's the general rule. While if you have, for example, a postsynaptic neuron that fires while the presynaptic does not, that strength would actually be weakened, right? So neurons that fire together, wire together, and that the connection between them will increase. And what we're finding is that when you apply direct current stimulation, neurons that fire together wire together more. Neurons that do not fire together still don't wire together. And so that's one way to maybe summarize it.
Great stuff. Are you happy? We've got loads more questions, but in the interest of time, do you want me to forward them on to you via email and then you can answer them directly there? Or
Sure, people are welcome to email me. I really appreciate these questions. They obviously touch on things that I did not explain fully, so I really appreciate them. And so yeah, people are certainly welcome to follow up. You can please email me them. People are certainly welcome to email me. I obviously really appreciate the interest and the questions, if there are any.
Yeah, we got about 20 minutes worth of questions still to go, so I'll let you go. Thank you again for enthusiastically giving this presentation, answering all the questions so thoroughly. I'm sure it's been really useful for the attendees, really useful for me. And I'd just like to thank you again. Really appreciate your time and your efforts.
Thank you for the invitation, and thank you to Brainbox, and thank you for everyone for listening and for your really good questions that helped me, I think, round out a lot of holes that were left at the end of my talk. So thank you for those.